This afternoon, as I say, we're going to start off with Jean-Philippe Uzan, who is going to be talking about the tuning of nuclear processes in astrophysical and cosmological context.
Great.
Jean-Philippe.
Am I supposed to talk about this? Great. Okay. Good afternoon. This is like a command. Actually, it was I was asked to talk about this because, as you know, and you said that just at the Khalil talked about that at the beginning of the conference. There is this book on fine tuning, and I was asked, to try to make a review on the tunings that we get in nuclear physics. And so I know we are a mixed audience of physicists, astrophysicists, and more philosophers. So the problem is that it's a highly technical problem. So I'll try to give you, I know it's good. I mean, I like technicalities because when I compute, I don't ask deep questions that I can answer, and I'm less depressed. Okay, so you say it's working, but not with me. Maybe you have to talk to the computer? No, look. Oh, he has Mike has magic fingers. Okay, I use my computer like that. Okay. So I'm a theoretical physicist, so when I try to understand nature, I know that I try to understand which laws of nature we want to use. And as you know, today the description of nature we have is based on the standard model of particle physics and on general relativity. We know this theory are not final theory. We have clues that they need extension either for experiments or for theory, that probably we need a quantum theory of gravity, that we have to extend the standard model in particular if we want to include massive neutrinos. But there are no such theories at the moment. They are candidate theories. So if we have to be conservative, these are the theories. They are both well tested by experiments. What are you doing with my computer? There are dangerous things on this computer. Okay, good. So what I will do for now is just to restrict to this series because I know what I'm doing and I know what are the domain of validities of this series. And of course, we will have to consider extension of them in discussion, in particular, if you want to discuss about fundamental constants and how they can derive from a more general theory. But there is no unique way in doing that. And if we start to study all the unification scheme, I would need more than the week to explain that to you. So now it's not working even with this one. Okay, I use my fingers. Okay, so no, I'm not here. It's okay. So what is important when we do cosmology is that if we think about the description of the Big Bang model as far as we understand it, and we stop, let's say, at Big Bang nucleosynthesis because this is really where we have a lot of information, you know that basically energies are such that we just need to rely on general relativity, electromagnetism, and nuclear physics. This is basically what you have to do. If you want to go deeper, close to the Big Bang, or to talk about inflation, I'm sure Jerome will do that. You will have to use quantum field in curved spacetime, and you will have many extensions to consider. But here, this is basically what you need to do. And this is good because it means that basically the predictions we have from BBN to today, they rely on physics, which is well tested in the laboratory, which makes that some robustness of what we do in astrophysics and in cosmology. So the influence of fundamental constant has been really well studied on these systems. And the idea is that you can find some physical system where when you change the value of some fundamental constant, the behavior of the output of the system dramatically changes. So that has been used in two different ways. The first is to put constraint on the variation, space and time variation on fundamental constants. And this is really for like what I would call with quotes, normal physicists, people like we were discussing about what is science, people who want to know how valid is the theory I'm using, because if you use a theory, this theory assumes that some parameters are constant. You vary your action with this supposed to be constant. You compare it to experiments, given the error bars you have in your experiments. Reproducibility of experiments tell you that this constant do not change. So if you see a constant, let's say alpha change by 10 to the minus 5, for instance, it will tell you that this is not a theory. You have to extend your standard theory. So this is more important when you love general relativity, as I do, because this is a test of the equivalence principle. And then, of course, you can use the study of these parameters to study the level of fine-tuning, because imagine that you change the value of some constant and some new phenomena appear, some phenomena that did exist before do not appear anymore. For instance, let's say nuclei are not stable anymore. Then it tells you that you cannot go further than what you... I don't have a pointer or whatever. It's just weird to talk like that. So it's important. Usually the constants, the constraint you would put on the constancy of fundamental constant are much deeper than this. Have you tried? Because either there is a fine-tuning with me, but okay. Okay, so what I want to take a minute because I'm talking about the equivalence principle. Rocky is so bright. About the equivalence principle, because today what's amazed me the most probably in physics, this is the fine-tuning. I mean, is it a fine-tuning? I don't know, but this is some coincidence that I find is the most appealing of all physics that I would like to understand one day, is the one concerning the equivalence principle and the universality of free fall. As you know, today it has been tested to the 10 to the minus 13. I would have loved to tell you something about the output of the microscope satellite, but data are going to be released in 5 days. What I can tell you is that it is supposed to go to 10 to the minus 15. And I cannot tell you whether there are some hints of whatever dilatons or so, or whether we just improve the constraint, but these kind of experiments will tell us that probably 10 to the minus 13, 10 to the minus 14 between the inertial mass and gravitational mass is something that we have to explain. This is at the core of general relativity. It's very important to test it. And we have no explanation because general relativity builds the equivalence principle in. You cannot explain it within general relativity. You have to take extensions of the general relativity and then to see what is the level of tuning to do that. I don't know, maybe most of you are more educated than I, whether there have been some anthropic argument for the validity of the equivalence principle. I would love to know that. Okay, so now so that was just like an advertisement because data are going to be released very soon. And took us a lot of time to work on this. So I'll go back to the thing that was developed by George, and because probably I discussed too much with George, so he put ideas in my brain that I still don't know how to deal with, about his hierarchy of structure and the fact that, well, if you start from fundamental physics, basically at each level you have a theory and it creates a space of possibility for theories of higher complexity to emerge and to be constructed. And you know, at each level, you have a different ontology. You don't, in particle physics, you will talk about quarks, let's say, in nuclear physics about atoms and so on, in chemistry about molecules. And you have to understand how these structures are related to the structure beneath. And what George tried to push for many years is that, well, basically the lower level sets the conditions for the higher level to emerge. And this one, they put constraints on the lowest level. If you take time, basically what is interesting is that all this structure, all this, you cannot get, for instance, chemistry at the onset of the universe. The universe is too hot, too dense. Molecules are too weak to survive. So basically you will have to climb all this scale of complexity, and this is basically what we say in popular talks, that, you know, the universe was hot and smooth and structureless, and basically this is a race of complexity. But you will have some time to wait for this to happen. And also it will ask a question about where in the universe you can climb this scale of complexity. And also what you see is that at some stages, you have some new concepts that appear. Like the concept of information. You cannot store information unless you have something which is stable enough to put 0 and 1. It could be spins or it could be electrons or whatever. You need something that is stable enough. If you are, let's say, a couple of minutes after the Big Bang, you cannot store information. Of course, you can have a notion of entropy, but it's a useless concept. You cannot store and reproduce information. So this, if you take the standard Big Bang theory, you know that temperature is decreasing with the expansion of the universe. And so the universe is very hot. The structures that you have are mainly, protons and neutrons before BBN and then nuclei. So you cannot do any chemistry here. And as you cool down, you will have nuclei appearing, and then you can do atomic physics, and then probably you can do chemistry, and so on and so on. And you cannot talk about any life before you are able to have some kind of atoms, molecules that are stable and enough of them in your environments. If I look at the structuration of the universe, here the universe is very smooth. We know that here typically the fluctuation of density are 10 to the minus 5. And then of course they will grow, you will have structure formations, and there will be a region in space, but very tiny region in space where you will form stars, and these stars will generate other nuclei, so that you can have to have a lot of complexity. So it means that all these places in the universe are very tiny spots. And this is the way I think we have to consider this hierarchy of theory in a cosmological context. So what is important in this series, there are different, for physicists, different things that you have to keep in mind, is that, as I said, there is a relation between the lower levels and the higher levels. Basically, the fact that the one determines the space of possibilities and the one gives the context. There are decouplings, and it's very important that we get decouplings in theoretical physics. It means that we can build some effective field theories, for instance, which means that you can integrate out all what you don't know. Imagine there is no decoupling and that you need to understand, if you want to do chemistry, you need to understand what is a proton, what is a neutron, and probably what is string theory. Probably we would not have got here in terms of technology, because as you know, we started physics by breaking stones, not by breaking atoms. So if you need to understand the more fundamental level before you can start at a low energy, then it's very difficult to think on a way to get handle of nature with the experimental methods as we are used to do it. And it means also that there are energy scales below which this effective theory gives very good representation of nature. And this is what I'm calling a good theory. So basically a theory which is coming with its domain of validity, and I know that in this domain, this is a good theory to explain a class of phenomena. So the question is that we have this hierarchy of complex level, and we're talking about fine-tuning. As was said this morning, fine-tuning for what? I think is a very good question, because as for evolution, selection can take place at different levels. You can select at the level of the cell, or the organ, or the body, or the species, and all these selections are taking place at the same way. Here we are fine-tuning at different levels. Which one has the most stringent? Imagine that I have tuned my series so that I get very stable nuclei and everything is fine. I got enough carbon in the universe. Does it mean that water molecule will have the good properties for whatever we need it to have? For instance, like the negative slope, so that when your ocean freeze, just the top layer is freezing and not the whole ocean, and life can survive big winters and so on and so on. Can you ensure that, or will you get an extra fine tuning? And this is very important because you would like to compare all these sets of experiments. So I will talk about the deepest level. So if we start by what we know, which is quantum chromodynamics, so QCD, we have a theory with quark, with gluons, we know symmetry group that we know SU3, and we have a set of constants. All of them are very well measured, and I think this is why it is a good theory. We can measure all the unknown parameters with error bars, and all the parameters today are known since we have detected the Higgs parameter. And we want to go from this to something like, well, let's say the Mendeleev table. This is the basics of what we get out of nuclear physics. We know what are the diversity of the nuclei, we know their lifetime, and we know the difference of the different isotopes. From astrophysics today, we know the main site in which these elements are formed, which is very important. Not only we know which one can exist, we know where we form them, and I think it's also a very important issue. For instance, only helium is formed during, significantly formed during the Big Bang nucleosynthesis, and then you have to go to different kind of stars, large stars, small stars, population 3 stars, or supernova. And there are some elements here that we don't know any process in nature that are forming these elements. They are very short-lived elements, but these ones, they have just been synthesized in accelerators. So the question is, how do you go from what you know in QCD to what you need to do when you do nuclear physics? And this is something which is really messy, actually. So if you take the same elements and now you make a plot with the number of protons and number of neutrons, you have this value of stability, which means that you have all these elements which are long-lived, more than 10 to the 15 seconds. And you see there is something I will come back at the end. I'm far from being a specialist, but I discussed that a couple of weeks ago with Michael Paul and Zvi Piran in Jerusalem. If you look at the actinide here, you see there are this kind of islands here, and you have to go from here to here. And how do you go there? Because you see, the issue is that if you go to a stellar evolution, you will not go beyond iron. All the other elements, you need neutrons to do that, and you have to have environment with rich neutrons. And you can climb this value of stability here, but to go to the heavier elements is something very difficult. And I will try to give an example. I don't know whether this is significant, but I want to share that with you. Some thoughts about the local environment. We have the GRB killers already. Maybe we need also something to have a good local environment to get this element close on Earth. So from a practical point of view, as I said, it's a very technical issue. If you want to understand any observables, what you usually need to do, you take this observable and you try to predict the value of these observables in terms of the fundamental constant that you have in your model and external parameters. This is standard physics. Usually what you do is that you assume that these numbers, they are taken from a book. Newton constant is 6.67, blah, 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 and so on and so on. And you try to know something, to infer something on the external parameter. What is the temperature? What is the magnetic field, the density, and so on. Here, what you will do is that you will assume that you don't know these parameters, and you'll try to measure them in the physical study system you are studying. So basically, you will have more parameters. If you like MC or whatever, if you do this big data cosmology today, you will just have more parameters to fit over, and you try to know whether you can measure this parameter with a given precision. So what is important here is to know what is the sensitivity of this observable to a variation of these physical parameters. Usually these parameters are not fundamental constant. Imagine I'm using the binding energy or the mass of the proton. I know that this quantity have to be expressed in terms of the constant I showed in the first slide. I mean, in principle, I should be able to compute the mass of the proton in terms of mass of the quarks and the coupling constant which enters through the binding energy. This is usually a very difficult computation. If you want to know what is the sensitivity of the mass of a proton to a change of the fine structure constant, is something which is still an open debate. I mean, we have been doing that with Keith Olive a couple of years ago, and also for geromagnetic factors. And according to the way you go from QCD to nuclear physics, you can get a factor 10 to the 2. So basically 2 order of magnitudes in the computation of the sensitivity here. So this is something which is still a very difficult issue, even though the two theories are well defined. So you see, in principle, you can. In practice, you get two order of magnitude in your computations. So the systems that have been used to set constraint on fundamental constant in astrophysics are listed here. Locally, you have atomic clocks and you have this quasar absorption spectra, which I will not discuss here. It's mostly QED. And what I will focus on is the production of light elements, so BBN and stellar evolution. And you see, when you want to jump to BBN, you want to compute the abundance of some light elements. And the output of your computation will depend on a lot of set of constants, which make the things actually very difficult compared to other systems. What is important also is to have a look at the space-time diagram. So we are here, and this is a past light cone. So basically, you go this in the past, and this is your BBN and CMB. So this is the size of your observable universe. And you see that your systems are located in different places, and the earliest we can get is BBN. Also, it's very important because usually if we talk about BBN, you see that what we are doing is to compute something average on the size of the observable universe, assuming it's an homogeneous universe, while most observation, I mean, spectroscopic observation are very local observations. So they may be also the use to enter the cosmological models and validity of the Copernican principle here in the discussion here. So when you do this model, it's very easy to design a model with dynamical fundamental constants. I mean, you have to take your fundamental constants, say they are dynamical fields, and just try to see how you can, out of this, you can write a well-defined field theory. But you have scales, and two things can happen. You can have variations in which basically you will get patches where you have different values of your fundamental constants, and that you have to compare this typical size with the size of the observable universe. In most theories, when this is smaller than the size of the observable universe, there is a chance that you can put constraint on this model, because you can observe different patches of the universe, and you can ask yourself whether the fine structure constant has the same value here and here, for instance. But if the size of the observable universe is smaller than this, so basically this is what I call a micro landscape. There is no landscape at all in this business. It's like, you know, you are working in a crystal, and the part you can observe is just one block region of a crystal. And then you cannot test directly this thing, because, well, you will observe just this value of the fundamental constant, and there is no way you can have access to the other patches. So this is not like, as Bernard was explaining, like a multiverse. You don't have to ask for yourself what is I mean, whether there are other universes and so on. What is important here is that you get different vacua in your theory. And of course, you may have at the quantum level some tunneling between one and the other. And the only thing that could happen is that basically close to here, there is a true, I mean, some part of, if you are in the false vacuum, tunneling to the true vacuum while you make observations. So let me come to BBN. So when you want to study Big Bang nucleosynthesis, you start typically when the universe is 100 MeV and you have protons and neutrons. And what you know is that the network of nuclear reaction, which I wrote here, and the important point is that you have to go through deuterium. And as you know, the binding energy of deuterium is very low. So at the onset of inflation, density is high, but temperature is too high. If you try to form deuterium, then the universe being too hot, it will be photoionized. And you wait for the universe to cool, but because it cooled, it's also become more dilute. So basically the probability of two-body interaction will decrease. And so you have like a small window during which you can form helium. And you can do that. I mean, this is what you do in cosmology lecture. Back on the envelope of computation, you get the 24 or 25. It's in your book, and it's in all the books in cosmology. You just start by that. Of course, you need to do numerics, and when you do numerics, you have one free parameter, which is eta, which is the number of baryons per photons, and you can compute the abundance of the light elements. Helium-4, deuterium, helium-3, and lithium-7. And we have observations. So this is the error bars for the observation of these elements. And what is new in this domain is that from the analysis of CMB anisotropies, you can get a direct measurement of eta, which means that you need to be in this vertical band. So you see here, this is in agreement for all the elements, but there are still this discrepancy for lithium-7. We don't know what it means. It has been debated in many conferences dedicated to that. Is it astrophysics? Is it fundamental physics? Is it whatever? There is no clue of the resolution of this at the moment. Now, if you turn to stars, in particular the first stars, you want to go from the initial conditions given by Big Bang nucleosynthesis. So basically, this is the main elements you have in the universe, to see how you go to heavier elements, in particular carbon, oxygen, and so on. But you first have to go through carbon, and the main route to go to carbon is to go to the triple alpha reaction. Basically, you take 2 helium to make beryllium, which is unstable, and beryllium can interact with helium to do this excited state of carbon, which then will be disexcited. So for this reaction, you can compute the reaction rate. And as you see, it will depend on this Q factor. And this Q factor will be a function of the resonance energy of this nuclei. So it will depend on alpha. It will depend on the nuclear physics. So these are the two main things I want to discuss. So if you go to BBN, as I said, this is the back of the envelope computation. But what is important is that you get the ratio between neutron and proton before the freeze out of the weak interaction, and you have a Boltzmann factor. So this Q is a difference between the mass of the neutron and mass of the protons. And then you start to form deuterium. It was important after the freeze out of the weak interaction, neutron will decay. So all will depend also, I mean, this ratio will also depend on the time before the freeze out and the time you start to form deuterium, and with respect, I mean, and in function of the lifetime of the neutrons. And the time this happens depends on your Einstein equation, Friedman equation. So basically here you have the energy content of the universe, and this is the expansion rate. And so basically you have this computation between the weak interaction and the cooling of the universe, which will show that the freeze out time will depend on the Fermi constant, on the gravitational constant, and the number of relativistic species. So you see, this is a fairly big computation. And so what you get at the end, you also need to take into account the dependence of the constant in the Coulomb barriers. And you have basically that the output of your computation will depend on a long list of constants, gravitational constant, Fein-Structure constant, and so on and so on. So if you do that, the first question you would like to ask is, which of these parameters is the most important? If I vary them independently, which one changes the result by the most amount? So this is the first thing you can do, and you change the mass of the electron, the binding energy of deuterium, the difference between mass of the neutron and protons, and the lifetime of the neutrons. And you see that the one which is the most significant here is the binding energy of the deuterium. And of course, you understand that from basic arguments I gave before. This is a bottleneck. If you change the binding energy, you will shift the time you start or your nuclear reactions. So this was in, when was it? 2006, well, 10 years ago. So we did this analysis 10 years ago. And amazingly, what we found is that there was a space here, basically, where the binding energy was smaller than it is in the laboratory, which could reconcile lithium with observation. So it was fine with helium-4 and deuterium, almost deuterium, and lithium-7. So this was 10 years ago. It doesn't work anymore because, as you know, the error bars on deuterium are shrink by a factor 5. So now this is no more a possible solution. And I think in the discussion we had today, I think it's good to speculate on the models that you have and try to see how far you can go with them. But it's good that you can have observation to exclude them, because otherwise, I mean, we could have all been arguing that, well, everything is gone with lithium-7, just required to have a lower deuterium energy. So when you do that, then you want to see whether there are other routes. And in particular, what important point in BBN is the fact that the A = 5 and 8 are unstable. So what we did is to try to model the fact that we have stable A = 8 beryllium, for instance, and see what is influence on the network. So we have to model all these nuclear reactions here. So to do that, well, you have to make simplification, and we use what is called the cluster model, or the Minneapolis model. Is basically you factor out the wave function of your beryllium-8 and carbon-12 in terms of the wave function of helium-4. And then when you do that, you can solve your Schrödinger equation and try to get the influence of a change of the nuclear interaction or the electromagnetic interaction, and to see how it affects the binding energy of deuterium and the resonance energy of beryllium and carbon-12. What is interesting is that you can even make the link with theoretical physics, because if you take the simplest nuclei, which is deuterium, there are different ways to compute the sensitivity of the deuterium element. So either this computation in terms of this parameter, or directly from a theoretical analysis, so you can relate this parameter to a change in the wave of the Higgs or the Yukawa couplings, for instance. So if you do that, then you do your numerics, and you see how, as a function of this parameter, which is a change of the nuclear-nuclear interaction, you change the resonance energy of beryllium-8 and carbon-12. And you see drastic things can happen if you take two large values, because you can have beryllium waves can become stable, you can have a d neutron which is stable, and d proton stable, and so on and so on. So this can have huge effects. So we didn't go that far, but we wanted to know what happened if beryllium-8 is a constant. So the first thing is, once you have this delta N, you can go to your data and see whether any hints of variation of these things. And you see that at the level of 0.1%, I mean, you don't see, I mean, astrophysics tell you that there is no such variation. And then the thing then is to try to go a little bit further. Try to push the parameter to see whether you can enhance the production of carbon, nitrogen, and oxygen. And there was two ideas behind that. The first is just standard astrophysics. We know that the abundance of CNO at the end of BBN is typically to 10 to the minus 5, and it goes through this kind of nuclear reactions. But you know that metallicity will affect the evolution of population 3 stars. They will change their lifetime, they will change the way they evolve either to neutron star or to black holes. And can you have higher metallicity at the onset of population 3 stars? That's the first question. And the second question, which is there a way to push your parameters that you produce enough carbon during BBN so you can start life even without having stars? I mean, that would be like maybe science fiction, but can we push the parameters to do that? So this is what we try to do. And you see, in particular, we try to see the effect of the 3 alpha reaction and the fact that the stable, so you see here, beryllium-8 becomes stable, to see how much it can affect the standard prediction of BBN. My slides are not in order, so this is where it is. So basically, no. Where is it? No, it's here. I'm sorry. Yeah, sorry. So this is a ratio between the two. And you see, you're still 6 order of magnitude below this 10 to the minus 15. So actually, you can push your parameter. You can put beryllium-8 stable. It doesn't change too much the abundance of carbon, nitrogen, and oxygen that you form during BBN. And the reason is that, well, the density is pretty low, and actually the duration of the BBN is very short, and this is why you can go very far and overproduce carbon, nitrogen, and oxygen. And I think it's very good news, because it shows that what you know about the initial condition for population 3 stars is very robust to this physics that you may want to change. There is another interdependency, if you ask about carbon and nitrogen and oxygen, is the fact that, well, you have to take into account more about 400 reactions, nuclear reactions, when you want to do that. And most of them, you don't know the reaction rates. For instance, there are reaction rates where the initial state, both initial states, are unstable states. So even in an accelerator, you cannot try to measure them. You have ideas about their cross-section, but they are huge error bars. So what we did is that we took all the reactions which are badly known, and we randomized the cross-section by 2 order of magnitude, I mean 4 order, 2 below and 2 above, to see how far with standard physics, given this unknown, we can boost the production of carbon. And this is basically what we get. So this is the standard value here. And you see, you can still go to 10 to the minus, so the standard is 10 to the minus 15. You can still go to 10 to the minus 12. So that's something which is important. And now people doing with astrophysics, nuclear astrophysics, try to get better value for these cross sections, because I think it's a very important thing for the understanding of the chemical evolution of the universe. And of course, when you do that, when you know if you want to do there, you can look at which reaction, what is the path in the nuclear network that leads to this value, and you can identify, the most important nuclear reactions that you want to control. So now, is it okay? So now if I do the same with stars, then you can have like much more important effects. The reason is that if you take population 3 stars, so now the density will be from 30 to 3,000 grams per centimeter cube. So you see there is like many order of magnitude with the one you have during BBN. And of course your universe is, your stars is evolving on a much longer scale. So this is what we try to do. And to do that, well, it was a huge project, so you have to start from the fundamental constant, use your model from nuclear interaction to get how your nuclear parameters are evolving with this fundamental constant. This is what I showed before. Then, of course, this is not what is important. You need to integrate that on temperature to get your cross-section, which you do. Then you get reaction rate, which depend on these parameters and temperature. Here is an example for the 3 alpha reaction. And then you have to put that in a stellar model. Stellar evolutionary model to see what is the effect on the stellar evolution, and you will get lifetime of the stars, the evolution of the Hertzsprung-Russell diagrams, and also the nuclear abundance of all your elements. So this is what has been done by, this is a huge team with people from Geneva and Brussels and Paris. And you see here an example of, so this is a standard Hertzsprung-Russell diagram, and this is what happens if you change the nuclear interaction. So this is the 3 alpha reaction rate. And in the end, what you do is that if you take some stars, so let's say you take a star, so this is for a 60 solar mass star with 0 metallicity, and you change the nuclear interaction, and then you look at what is the abundance of your stars, of the element you produce in your stars. So basically, we know that we want to have like some carbon and oxygen, so this is the standard value here. But you see that if the nuclear interaction is stronger, basically your oxygen will be burnt and you've just finished with almost just only carbon. If it's lower, then it will proceed. Your oxygen, at the end, what you will get a core of magnesium. So you see that you have a small window. So basically, like the order of magnitude, if you want to say that you want this ratio to be typically of order 1, so basically to be in this region, you see that the tuning of on the nuclear interaction is typically of 0.1%. So this is the level of tuning you need if you want this carbon and oxygen to be produced in this kind of stars. Okay, as you said, all this there are like intertensities on that. Maybe there is a factor 10 somewhere here, but this is the order of magnitude that we have to keep in mind when we talk about fine tuning for these things. So now I'll come to my conclusions. Yeah, I'm almost on time. So as I said, so this is the chapter I wrote in the book where you have all the technical details to see if you take BBN and stellar evolution, what is the level of fine-tuning that you get. It's very important just for the elements, because if you take elements, well, you can compute their lifetimes. You know that it has been used to put constraint on the variation of fundamental constant, the fact that some nuclei, which were alpha or beta decayer, could turn from stable to unstable, and some of them are very sensitive to change of some constant. So that goes through the computation of the binding energies. There are other effects coming from also QCD, some QCD effects, like if you want to compute the gyromagnetic factor, this is an open issue. How do you get the gyromagnetic factor from QCD? And of course, it may seem that, well, who cares about gyromagnetic factors? But if you start to do chemistry, you have quantum mechanics and you have couplings and so on, and stability of some molecules may depend on that. And we have no idea at the moment how this geomagnetic factor depend on the QCD parameters. We had some early work with Fenglo and Kisoliv, but this is still an open problem. And there are these environmental effects. So here is, I'm not sure about what I'm saying now, so don't blame me if it's completely wrong. So as I said, there is the actinides which are here. And the question is, how do you get from, let's say, here to this part? And you see, like, there is this cut here where you have very unstable nuclei. So you get to go to jump here. To produce them, basically, what you need to know is that, if I understood well, you need about 150 to 200 neutrons per nuclei if you want to climb up this region. So where do you find these neutrons? So there are two theories, but Abby should know better than I on this. So now I'm very fearing about what I'm going to say. So either there are type 2 supernovas, or there are the collapse of binary neutron stars. And this is basically the two environments that has been considered basically to synthesize these actinides here. And in this article, which I came through very not far along, they claim to be able to prove that from study of the correlation of the abundances on Earth, on rocky planets on Earth, actually that the way to go here locally for us was through the merger of binary neutron stars. And that sounds to me very interesting, because we were discussing about the possibility for this element to exist and be stable, and this is what physics will tell you. But you have to be sure that in your local environments, you had the conditions to go there. I don't know whether actinides are really important for anything. Maybe for civilization to power nuclear energy, that could be, I don't know whether this is something, the kind of tuning you want to know, but we have been discussing about what is life, what it is to observe. I don't know whether we want advanced civilization. For years, it was useless for life to evolve on Earth, but at some stage, we relied on these elements. And you see that here you have some elements that the presence of which depends on the nature of the local environment. I don't know whether it makes sense, but I think we have to distinguish about the fact that what we can tell with physics is whether some basic elements like atoms, nuclear, are stable, unstable, whether you can produce them, or whether they have the good characteristics, and the environmental factors. And this is very difficult to distinguish between the two. So this is why I wanted to say with these environmental effects. So now the question is to compare this level of tuning with the tuning on other parameters, and as has been studied, if you go to the nice review by Luc, he has a list of all this, and also in the paper by Bernard. What is important to keep in mind is when you do that, you are just doing a local analysis. You see, I've not changed the theory. I've taken the standard theories and I've allowed myself to slightly change the parameters. What if the physics is completely different? If it's not SU3 cross SU2 cross U1, can you tell anything? Here I know the physics, I have experiments, I can measure my cross-section and calibrate my computation with experiments to know that what I'm doing is not completely wrong. If I'm playing with another QCD theory, I have no clue how to do the computation. I know there have been some articles, I don't know how to trust them and how to check them. Given the difficulty to do with a theory we can test, I'm very doubtful about trying to understand whether another theory which is not based on can lead to a viable nuclear physics. What is important also is the importance of correlations. What we have seen is that if I take the constant one by one and I vary them, I can get constraints. Sometimes you know that these constants are correlated. If I change alpha, I will change the mass of the proton. I will change the mass of the neutrons, for instance. So if I don't take all this correlation into effect, I can go to wrong effects. Sometimes I have correlations, sometimes I have enhancements. If you want to do that, it's very difficult. For most of the constants, you don't know how to take into account the effect of let's say the Yukawa couplings on the protons, on the neutrons at the same time. It's something which is very difficult. And as I said before, just to finish, so in this study, what I'm interested really is the level of tuning for basic structures such as nuclear molecule to exist. And this will tell us how it affects the space of possibility for higher levels. It doesn't tell that you will go or not go there, but it's really a study of the structure of the theory, given what we know as the most fundamental theory today. And how far can we climb that? I have no idea. I'm sure George will tell about that. Unfortunately, I will not be here to listen to his talk about what we have been trying to do, and also with David to go one stage above that, and to see what is the effect of the change of some of the constants, so the alpha and the ratio between mass of the electron and mass of the proton to the structure of molecules. And basically, the question would be to ask, if we get tunings, are they stronger or what is considered? Weaker, or weaker than the one you get from, let's say, producing carbon in stars. If you end up by the fact that once you have formed the carbon in stars, structure of molecule, you are sure they are fine. Then you don't worry about them. If you see that you have a sharper constraint, then it tells you that you will have to take out all this stage of complexity, which makes the discussion of fine-tuning much more difficult to deal with. Okay, so this is basically it. Thank you.
Okay, time for a couple of quick questions. Yep.
Oh, so just a little bit more detail on your results concerning the carbon to oxygen ratio in the massive stars. I think that, if I'm not mistaken, the ratios you get will depend on solar mass. So if you have a whole range of stellar masses, you could get different results. In particular, you can get carbon from one star and oxygen from another. And another thing to put on the table is that AGB stars, asymptotic giant branch stars of intermediate mass that don't blow up, are often carbon stars. So they produce lots of carbon in their winds where it condenses out. So my only point is to ask you two things. One is what you did in terms of masses, and second, just to point out that stellar evolution has a lot more channels than a lot of people realize. You probably do, but not all of us.
Yeah. Sorry if I was fast on that. So
you were short for time. I just wanted some detail.
You're completely right. This is where things start to be messy. I mean, the number of channels that you can have depend on the mass of the initial metallicity, whether you are winds, whether you have companions, and so on. You can get many routes. So this is what I mean. This is why I say, this is an indication of the typical level of tuning, and so we reduce to population 3 stars because in some sense they are much easier to study. We know the initial metallicity, and here we took star from 10 solar masses to 60 solar masses typically in our analysis, but that was just because at the time we were interested by other questions which are related to black holes and so on. But anyhow, so I agree with that, and this is why it's very difficult. We never use that to put any constraints on variation of fundamental constant because there is no way to do that. So here the idea is basically to have a flavor of the sensitivity of these stars and production of this element in these stars. If you shut down the channel, are there other channels? Well, we have to find. I mean, you have to do the same exercise for each kind of stars, and it's like huge work. And this is why we didn't do it. But it would be like a couple of PhD theses to do that. Here is basically to show what you have to do on a single case, which you can master all the chain of. I mean, going from theory to the computation. It's like it required many teams. I mean, we were working with Geneva Observatory to use the stellar code, people in Brussels for the nuclear astrophysics, and our group for the theoretical physics, which is kind of, you see, like 10 persons. And you cannot be specialist of all these things at the same time. So it was really to get some numbers and have a way we trust these numbers, and also where we can see whether there are correlation between the variation of different constants. That was really, the goal here. And I don't want to oversell that if I was too fast. Just
Yeah, clearly CNO synthesis and probably all the way up to iron is critical for planets and life as we know it. But I have a hard time thinking of any really critical role in making planets and life work for anything above iron. In fact, even all the organometallic enzymes I'm aware of that make life and photosynthesis work are all on things iron and below. And what's in our atmosphere and the geochemistry that keeps our atmosphere habitable, that's all based on the lighter things than iron. The one case I can think of where planets would be really different without the things beyond iron is that the radioactive heating that helps keep our plate tectonics going relies on the long-lived radioisotopes. Yes. Without that, you would still have plate tectonics and recycling, but it would be just relying on primordial heat. So it's not clear that would be a showstopper, but it would be the one case for wanting to have some of those things around. Atomic warfare being the case for not having them around, I guess.
Yes, that could be good, that could be bad. No, what I was saying is that, of course, that was an example of, which was very, very nice, of the environmental effect. They exist, they are long-lived, but you need to have something in your history that tells you that they have to be produced at some stage. It could be completely irrelevant, but you don't know.
Okay, we'll have chance to ask Jean-Philippe more questions at the round table later, but let's thank him for now.
Thank you.